of knowledge today. And over to you, Dr. Shrikant Godse.
Thank you, Hina, first of all. And thank you, Principal Ma'am and Coordinator of FDP, Dr. Murnal Sane, for giving me this opportunity to introduce one of the best, great person, scientists. Good morning, everyone. Welcome you to all 5 days FDP. Before introducing our today's speaker, I would like to share one quote of our former president, Dr. APJ Abdul Kalam. What he say, learning gives the creativity, creativity leads to thinking, thinking provide you knowledge, and knowledge make you great. With this thought, I will privilege to introduce speaker of the session, Professor B.M. Bange. He obtained doctoral degree from National Chemical Laboratory in year 1995 and spent several years in Tohoku University, Hokkaido University, Japan on various research positions. He joined Institute of Chemical Technology as a professor of industrial and engineering chemistry in the year 2003. During 2009 to 14 and May 2021 onward, he is the head of the Department of Chemistry at Institute of Chemical Technology. He is also Dean of Infrastructure, Campus Development since 2014. Professor B.M. Bange has contributed in the area of catalysis in organic synthesis for activation of small molecules like carbon dioxide, carbon monoxide, and hydrogen for various reactions. He has developed novel strategy for various reactions like Heck, Suzuki, Sonogashira coupling reaction, their carbonylation form, hydroformylation, amino carbonylation, alkoxy carbonylation, amination, and hydrogenation, etc. The work is focused on developing strategies for catalyst product separation and catalyst recycle. He has developed several homogeneous transition metal catalysts for this reaction and solid base catalysts for carbon dioxide fixation reaction. He is also active researcher in the field of nanoparticle synthesis and its catalytic application and enzymatic catalysis, etc. He has published 521 research paper international journal, and in this include one publication Nature, JAC, JOC, and many high impact factor journal, and also 28 book chapter, 34 patent, and he has received more than 14,448 plus citation with H index of 61, I-10 index of 311 with huge profile. He has guided 46 doctoral students and currently guiding 15 scholars of doctoral research. He is a fellow of Indian Chemical Society, Royal Society of Chemistry, Biotech Research Society of India, and Maharashtra Academy of Science. His name is listed in the top 2% scientists in the world as per analysis published by Stanford University, USA, in the subject of organic chemistry. And today today's topic of presentation is green chemistry, development of experimentally benign synthetic procedure for organic synthesis. We are grateful to have you here, sir. Looking forward for this session, informative. Thank you so much for accepting our invitation. Now screen over to you, sir. Thank you so much.
Sachi.
Share my screen.
Can you just take the control of navigation to you?
First of all, I'm thankful to Dr. Mrunal for inviting me to deliver talk here. Also, Dr. Shrikant for introducing me. There is one small correction. My number of publication is 437, not 521. It should not have wrong figures.
Okay, sir. So I checked from Google Scholar. That's why.
Google Scholar, yeah, but I normally consider publications listed in SCI journals. Other publication I don't count.
Okay, I make corrections, sir. Sorry, sir. Okay.
Okay, fine. So that's apart. Today I will talk on green chemistry and its role in organic synthesis, particularly pharmaceutically important molecule. Green chemistry in future will play a lot of role because You know that current manufacturing processes for all APIs and pharmaceutical molecules involving lots of complicated procedure which produces lots of waste, and disposal of such waste is also problem, and they are not environment friendly. So from that perspective, one should look into the methods which can give you green and environment friendly. So before starting those details, I would like to have short introduction to this subject, that is organometallic chemistry. And afterwards, we will see how we can use organometallic chemistry in drug synthesis. So first part of my presentation will be dealing with some basic concepts related to organic chemistry. Some of you may be aware about that, but for those who are not aware, uh, I would like to introduce that part. Okay. So at ICT, we are working on various types of catalyst development. For example, homogeneous catalysis. We also work on catalyst product separation techniques in homogeneous catalysis. We use non-conventional techniques like ultrasound, microwave for those reactions. Also, we work on supercritical carbon dioxide and reactions in supercritical carbon dioxide, ionic liquid. And another core area of interest is CH activation, carbon monoxide activation, hydrogen, syngas chemistry. So today I will focus mainly on the last part, that is CH, CO and H2 application for pharmaceutically important intermediates. So as I told you, we are working on homogeneous catalysis, and you know that in homogeneous catalysis, organometallic compounds are involved, in which central metal is quite often surrounded by either organic or inorganic ligands, and these ligands plays a significant role in development of those particular catalyst, and this catalyst development is a very critical part when you want to do the reaction. So the catalyst modification by changing the ligand environment plays a crucial role there. And most of these catalysts are important because they are selective. For example, I have taken here two reactions in which you can see that hydrogenation, it can have two sites. You can have chemoselective catalyst which can functionalize one of the functional group, or you can have regioselective catalyst which will give you the region specific selectivity. So such type of transformation is possible with the help of those developments in the catalyst. You can also develop enantiomer selective catalyst. I will give you the example of dopamine synthesis, in which you can see that how enantiomer selectivity plays a role and how one can develop enantiomer selective catalyst. So why selectivity is very important? Because if you can develop a catalyst which gives you the high selectivity, it means that you are not producing any other products, and that reduces the waste in the total process, and workup of the total reaction part will be very less. Typically, when you work with homogeneous catalysis, we have two different types of catalyst, that is hard catalyst and soft catalyst. In soft catalyst, what happens, you have a metal complex which is surrounded by different types of ligands, and those ligands plays a crucial role in development of those catalysts. Other type of catalysis is hard catalysis, in which we typically use acid or base, and those acid or base catalyzed reactions are possible using those type of hard catalysis. So all Friedel-Crafts reactions, oxidations, epoxidations, all those things are possible using hard catalysis. But today, which part which I will focus on is a carbonylation, hydrogenation, and oligomerization, because most of the development currently happening in this area, and hard catalysis, rather than, it's well established fact today. When you use any catalyst, it undergoes following types of transformation. For example, you prepare some catalyst, and we can say that it is a stable 18 electron complex. When you dissolve such complex into the solution, it forms unsaturated 16 electron complex. And once you have unsaturated 16 electron complex, it can interact with your substrate to form another saturated 18 electron complex. Now, once you get your substrate docked to the catalytic sites, this substrate can undergo different types of transformation on the catalytic site, and again it releases the product, and again it comes back to the another 16 electron complex. So this cycle will continue. So what we have to look for, that we should have catalytic cycle continue, your substrate is in and product is out, and this cycle should not get disturbed. Otherwise we can see that this particular catalyst is a poison catalyst, and therefore when we develop this catalyst, we have to ensure that this cycle keeps on going. Although I showed here 4 steps, it doesn't mean that it will involve 4 steps. It's a multi-step process in which catalytic cycle completes. And from that perspective, we can see that some reactions based on which how this catalyst can work. For example, if you take some catalyst which is showed at the center, now you can see that various substrates were attached to this catalyst. For example, methyl group is there, carbonyl group is there, olefin group is there, hydride is there, and they can undergo different types of transformation. For example, one can have dissociation of the ligand to produce another catalyst. This can interact with another substrate, so it will go to the different types of catalytic cycle. Or you can see that this CO is inserted between this metal and CH3. We can say that this is a migratory insertion. So this CH3 can go here or CO can go here. That's why we call this as a migratory insertion. So we can see that this metal alkyl becomes metal acyl, and you can very easily get the acylated product resulting from such type of complexes. Why only these two? There is also possibility that this hydrogen can transfer somewhere. So we get beta elimination and we get this product or you get this product. So hydrogenation reaction, this step is important. You can do the hydrolysis of the complex to produce such type of species. You can add some another new molecule on this tetrahedral complex to give octahedral complex. So we can call this as an oxidative addition, because metal gets oxidized and addition of another new ligand happens, and that's why we call this as an oxidative addition. If you see that reverse of the oxidative addition, we will call it as a reductive elimination. So these are some basic steps involved in any catalytic cycle. So based on this, we can see that many reactions possible. For example, typical hydrogenation of olefin. Olefin hydrogenation, what happens? Olefin plus hydrogen giving you the alkane. Fine. So this is the Wilkinson complex which shows you the hydrogenation complex. It's a very well-known hydrogenation complex. So what will happen when you add hydrogen to this complex? It will give you the oxidative addition reaction, and you get splitting of this dihydrogen into 2 hydride species. And after that, dissociation will happen, which creates a vacant site on the complex to which substrate like olefin can interact, and you get such type of complex. Afterwards, migration of this hydrogen will happen on this olefin. So this metal pi bond will convert it to metal acyl species, metal alkyl species, and after reduction, this hydrogen will again transfer here. You get alkane. So alkene gets this alkene gets converted to alkane, and that's why we call this as a hydrogenation reaction. It's a simple reaction. You may think how we can use it industrially. I will tell you that also. Before going to that, you should know that the role of ligand. For example, I have given here phosphine. Suppose I do some substitutions on this phosphine ligand. For example, if it is substituted with chlorine, reactivity will reduce. If it is substituted with electron donating group, reactivity will enhance. So this observation, just keep in mind. So based on that, we can have different types of hydrogenation catalyst. For example, this is the first generation Wilkinson hydrogenation catalyst, which can give you the hydrogenation of terminal alkenes very easily. Then Schrock-Osborn, the next generation catalyst, which gives you very high activity. But these catalysts were not effective for the hydrogenation of internal olefins. You can see that they were not performing for internal olefins. So later on, Crabtree developed, instead of rhodium, he put iridium, and we can see that the catalyst which can give you the hydrogenation of all sorts of substrate. So what he did very simple trick. If you look for the reaction mechanism, this step is very crucial step in which alkene adds to the rhodium. Now, the size of rhodium is such that it cannot interact with the crowded alkenes or internal alkenes. So, Crabtree changed the size of this metal, replacing this rhodium with iridium. Now, access of the crowded olefins like internal olefin is possible, and therefore, this catalyst is effective for all sorts of olefins. This dopamine can be possible. It is possible to synthesize using this particular ligand. So the reaction involves, this is the precursor for dopamine synthesis. This is the chiral molecule. So how we can synthesize? He has designed this catalyst. Now why designing of this catalyst is important? We can see that one side of the catalyst is blocked. So substrate will have access from only one side. Now from previous knowledge, we know that if we put methoxy group, reaction rates are enhancing. So he put methoxy group on this particular ON. This is ON. And because of that, it gives you the highest possible reactivity also. Now, let us see how it works. For working of this particular complex, can you see this slide?
Yes, sir, it is visible. Yes,
Okay,
sir.
so as I told you, one side of the catalyst is blocked here, and then hydrogen comes into the picture. It will give you the hydrogenation product, and this is your substrate for the dopamine. It can have two possibilities. It can interact with the catalyst in this fashion. One is SI interface, another is RE-RE interface, means top side and bottom side, both interfaces are possible. We can see that therefore we get two types of possibilities when this substrate will interact with this particular complex, and one of them will remain in the solution. It doesn't go anywhere else, but one side attack will go further for hydrogenation. You can see that H is added, and the previous method which we have seen that hydrogenation happens here, and you get typically L-DOPA using reductive amination step, and your catalyst is generated back. So this catalytic cycle will continue, and hydrogen and this substrate will come into the catalytic cycle, and you get the dopamine synthesis very easily. Now one question people will ask, if we are using such complicated rhodium based catalyst, how it can be separated? Fortunately, novels found that this catalyst is possible to separate by just precipitation technique. What happens during the reaction, this product dopamine used to precipitate from the reaction mixture, and mother liquor of this catalytic solution always keeping the catalyst in the mother liquor. So one can very easily separate the catalyst from mother liquor in the mother liquor, and the product get used to be separated, and today this is a commercial process for dopamine synthesis based on the homogeneous catalysis. Anyway, we'll see some more methods using such type of catalysis. Another is isomerization. You know that menthol is also artificially can be produced using the help of catalysis. For example, for that isomerization step is very important. Suppose you have some complex. I have not given the details of the complex here. When such complex interacts with the olefin, it forms pi bond. We have seen that in the case of hydrogenation catalysis. And after that, this hydrogen gets transferred to either this side or this side. You get vacancy on the metal. So metal pi bond converts it to the metal alkyl bond. And again, it can convert. It can also take hydrogen from other side. You can see that terminal internal alkene and it gets released. So in a way, you can do isomerization of olefins using such type of catalysis very easily, and this step is used in menthol synthesis. How? We will see that. This is a process which is developed by Professor Noyeri, another Nobel laureate for synthesis of artificial menthol, in which myrcene, which is a commonly available bulk quantity product, is used, and several catalytic steps were performed, in which olefin isomerization is involved here. You can see that, and you get here very crucial step wherein olefin isomerization happens, and you get your product, that is menthol, very using two types of catalyst. One is ruthenium binap, another is ranitidine hydrogenation, and menthol can be produced. Today, this is a commercial produced at Takasago Industries in Japan using such type of catalysis. Another large-scale application of homogeneous catalysis in industry, which involves carbonylation of methanol to acetic acid. I will not go into detail, but let me tell you, you can produce acetic acid using such type of catalysis. For example, if you have rhodium complex, this is methanol. Again, you have oxidative addition here. After oxidative addition, this methyl migrates over this carbonyl. It will form metal acyl. Again, addition of ligand and reductive elimination produce CH3COI, which this is CH3COI, reacts and hydrolyzes to give you the acetic acid. End reaction will be methanol is converted to acetic acid. This is one of the largest scale application of homogeneous catalysis in industry, and today industry is practicing this for large scale production. Same way, you can produce acetic anhydride also. Instead of methanol, you take methyl acetate and do the same chemistry, you produce acetic anhydride. Again, Eastman Chemical has a plant for acetic anhydride production using this particular process. Another application involves hydroformylation, in which olefins can be converted to aldehyde very easily in the presence of syngas, and you can see that hydroformylation gives you the aldehyde products very easily. Otherwise, by conventional organic chemistry, synthetic organic chemistry, this is very difficult. So I will not go into details about the catalytic cycle because that was not our today's objective. Next important part from the homogeneous catalysis, which is useful in drug synthesis, that is coupling reaction. And 2010 Nobel Prize is also for coupling reaction. So this is based on the same chemistry. For example, you can have Stille coupling, Negishi coupling, in which you will have different types of carbon-carbon bond formation reaction in presence of palladium catalyst. For example, you can take aryl or vinyl halide, react that with organotin complex, and you get the coupling of the R dash, and you get the coupling products. So formation of coupling new carbon-carbon bond is very important, and that is possible with this coupling reaction. There are 5 important coupling reactions which I had listed here. That is Stille coupling, Negishi coupling, then Suzuki coupling, Heck coupling. All these are very important. For example, Suzuki coupling, you will have aryl boronic acid, and aryl or vinyl halide will give you the coupling product. You can take Heck reaction. You will find that internal alkenes can be formed, and many more. So many coupling reactions are important, and therefore they play a significant role in the synthetic organic chemistry. Again, I will not go into details of coupling. This particular reaction, Heck reaction, finds lots of application. For example, you can take alkene and alkyl halide. You can see that internal alkenes are formed. So we'll see their application in drug synthesis in some more examples. You can see that you can literally couple any alkyl halide or aryl halide, and you can see that the coupling products are formed. And these are some applications. In Sonogashira coupling reaction, instead of alkene, you can take alkyl, and you can get the internal alkenes very easily. Then in olefin metathesis reaction, you can have olefins. You can take one set of olefin and produce another sets of olefin very easily. Otherwise, by conventional synthetic organic chemistry, this is very difficult to have preparation of olefins using such type of techniques. And there are many more olefin metathesis reaction in which Grubbs catalyst is well known. In Grubbs catalyst, what is important that you have metal and alkene bond, and this metal and alkene bond plays a role in formation of new coupling reaction. How? We can see that here, this is metal and alkene bond, and you have this olefin which interacts with this metal. It will form four cyclic ring containing four atoms like this, and this will collapse in a different way, which will produce one set of olefins. Again, this will carry forward, this set of olefins forms, and you can see that two different sets of olefins are possible from propene very easily. And based on that, Grubbs catalyst is developed for olefin metathesis, many more applications. So all these reactions, which is a basic reaction, some of you may be knowing all these things, and we'll see that how we can use it in a organic synthesis. So from that perspective, today I will talk on how molecule like carbon monoxide can be used for synthesis of various drug molecules. For example, if you want to prepare aryl ketones, and typical reaction people will perform is a Friedel-Crafts reaction. And if you want to have Friedel-Crafts reaction will have lots of problem because it can't work with the inactivated substrates. You need always activated aromatic rings. Second point is it needs stoichiometric quantity of aluminum salts which are produced as a byproduct. You need hydrolysis also there. So considering the Friedel-Crafts reactions disadvantages, carbonylation technique can be very useful, and you can see that using carbonylation, many such molecules are possible to synthesize using this particular tool. For example, oxybenzone, you can see that this carbon monoxide in red is possible to derive from the gaseous carbon monoxide. Same way, phenstallene, dioxybenzone. Then this is another anti-cancer cytotoxic uracil analog. You can see that this is a CO. Another anti-inflammatory and analgesic molecule is possible to synthesize. So you can see that these type of molecules are possible to synthesize using carbonylation technique. There are some more examples. You can see that this molecules. You can see that here many CO-based molecules are possible to synthesize, and this type of technique of carbonylation will be useful for preparation of such type of molecules. So let me focus on how carbonylation can be useful. You can see there are a number of drugs in which you can see that CO is there, and current methods of preparation of all these molecules involve Friedel-Crafts reaction or some complicated multi-step synthesis, but with the help of catalysis, you can do this in a few steps very easily, and therefore in future, if you want to develop such type of molecule which involves CO, will be really useful. It's let me tell you, handling CO is not at all difficult, because if you use high pressure reactors and if you take proper precaution, carbon monoxide gas can be handled very easily. It's already handled very well in the many petrochemical complexes in the large quantity. Many people feel that carbon monoxide is toxic, poisonous, we should not use. It's not like that, because if you know the technique how to handle it, it's very, very easy. Second point is that it reduces lots of multi-step synthetic products into very few steps. And you have seen that so many molecules which involves CO is possible to using the carbon monoxide chemistry. You can see that multiple. I have numerous molecules, but few of them I have showed it to here, and you can consider many more examples like this. So let me focus and tell you my own work in the carbon monoxide based reactions, and they are really useful or directly applicable to the synthesis of these molecules. I have shown many of these molecules synthesized in my work, but I would like to focus on some modern reactions which I did. For example, here we have developed a amino carbonylation reaction. Now you can see that here aryl halide and tertiary amine Now, what is the challenge here? That carbon and nitrogen bond is very strong. It is very difficult to break. So we took this challenge and we have seen that tertiary amines can be coupled with aryl halide, and you can see that amides can be produced very easily. And this CO is coming here. This is CO. This is this CO, and oxygen is required for this cleavage, and you end up with such type of amides very easily using palladium catalyzed amino carbonylation reaction. And the beauty of this work is you use palladium on carbon, which is a heterogeneous catalyst. You can separate it very easily after reaction by simple filtration, and you can reuse it again and again. So let me tell you how we have performed this particular reaction. So this is the reaction. The challenge is to break CN bond. So we have done multiple reactions. We can see that triethylamine we have taken, and we have substituted this aryl ring with many types of substituents, and most of these substituents works and give you the reasonably good yield for amino carbonylation reaction. You can see that again here also we have done exploration with respect to amine counterpart. Previous exploration was with respect to aryl counterpart. We can see that all this you can vary and you can get the corresponding amides very easily using palladium on carbon catalyst. And as I told you, this catalyst is recyclable. You can recycle it n number of times. Of course, you can also use continuous phase reactor to have continuous production of such type of molecules. This is a typical reaction mechanism. The steps are similar to those what I told you earlier: oxidative addition, reductive elimination, so and so on. In the next step, what we did, earlier I used aryl halides. Now instead of aryl halides, I have taken here alkynes. And you know that I had showed you the importance of this molecule in previous slide. So you can produce the coupling product involving carbon monoxide using similar technique. The catalyst is again same, that is palladium on carbon, and potassium iodide is a promoter in this particular reaction, and you can produce these molecules which are known as alpha beta alkenyl amides, and they have applications in pharmaceutical intermediates. So we have produced several types of such type of molecules, and we have varied both the components, and all the components give reasonably good yield for this molecule. Again, this catalyst is recyclable and we can recycle it n number of times. Then, what is the challenge in homogeneous catalysis? One is how you can able to recycle your catalyst. Otherwise, if this catalyst remains with the solution, it is not commercially affordable, because these are expensive catalysts. We have seen that in case of dopamine synthesis, the catalyst was remaining in the mother liquor, and therefore you could able to separate it very easily. Whereas in previous two examples, catalyst was heterogeneous but acting in a homogeneous fashion, but finally it was coming back on the carbon support, and therefore we could able to separate. Here we have developed a different approach. Here we have developed a catalyst which gives very high turnover number. You can see the turnover number here is 10⁹, which is unusually high. So such a small, even ppb level concentration may be of this catalyst, and therefore you can retain this catalyst in the solution, or you can destroy this catalyst in the solution, because it has already performed much beyond your expectation. And this is another approach. You can have a catalyst with very high activity, very high turnover number, and this is what we have followed here. So in this example, you can see that we have coupled aryl halides, carbon monoxide, and aryl boronic acid, and you have produced aryl diaryl ketones. As I told you, if you want to prepare these molecules using conventional organic chemistry, you need Friedel-Crafts acylation or alkylation reactions, particularly acylation reactions. So if you want to do Friedel-Crafts acylation reaction, they are not working with the aromatic rings which are deactivated. In this case, that limitation is not there. Also, you don't produce stoichiometric quantity of salts. So these two major advantages when you produce biaryl ketones using carbonylation technique. And from that perspective, this is very important. Now, suppose one may ask question, suppose I reduce this carbon monoxide, I remove this carbon monoxide, what will happen? I can get coupling of this very easily, and this is known as Suzuki-Miyaura coupling. So this catalyst is bifunctional. If you don't use carbon monoxide, you can get Suzuki-Miyaura coupling. If you use carbon monoxide, you can get the carbonylative Suzuki-Miyaura coupling. And finally, you produce biaryl ketones. And from biaryl ketones, you can prepare many other things. And this catalyst shows very high turnover number. That is the beauty of this. So how to prepare this Palladia cycle catalyst? I had prepared many such type of catalyst, and they are having very high melting points, good thermal stability, they are air and moisture stable. Whereas if you take conventional phosphine-based complexes, if you expose your phosphine-based complexes to the air, quite often they degrade because phosphine have tendency to get oxidized. In this case, this doesn't happen so easily, and your catalyst is having good stability. So prior to that, Bradford has published a work on Bradford catalysts which are used for Suzuki coupling reaction. He didn't use it for Suzuki carbonylative coupling reaction. Also, there are some more Palladia cycle catalysts were known, that is ruthenium phos, dinormyl phosphine Palladia cycle. Some catalysts were known. So taking clue from the previous work, we have developed our own Palladia cycle catalyst, and which gives you very high turnover number. So this is a typical cycle. You can see that we have explored the turnover number, and we could go up to 10 raised to 6, some cases 10 raised to 9 turnover number very easily. And this gives you the comparison also. Then also we have substituted this R and this R, and you can see that all types of substituents are possible. In all cases, you get very good turnover number, and you get the coupling products using carbonylation technique. Now, one may ask question, instead of iodine, if we take bromine or chlorine, what will happen? Let me tell you, chlorine is not easy to activate because this carbon-chlorine bond is a very strong bond and which you cannot break. But bromo, to some extent, it is possible. We could have bromobenzene and aryl halides, aryl boronic acid. You can get up to 60% yield if you take bromo. But with iodo, you can go 100% yield. With chloro, you don't get any conversion. So that study also we had performed, and this is a limitation with respect to chloro. Chloros are cheaper. Another molecule which is of interest is carbon dioxide. So we have seen that how carbon monoxide can be used for synthesis of different types of pharmaceutically important molecules. Today, carbon dioxide is also a problem because all of you know that this is a gas which is responsible for global warming. So research is going on how we can utilize carbon dioxide. Of course, using carbon dioxide to chemical is a very small effort because we produce huge quantity of carbon dioxide, and therefore, how we can activate carbon dioxide? For chemists, it is a challenge because you know that carbon is a highly oxidized form which is not so active. How to use it for some transformation? And from that perspective, we have done some work with respect to CO2 activation, and let me share, and particularly I have focused my work on pharmaceutical application where we can use for the synthesis of pharmaceutically important molecules. For example, you can see that here peroxidazole. So here this particular heterocyclic ring is possible to produce using CO2 technique, but I will tell you how. Then we can see that cyclic carbonates which are produced or oxazolidone molecules. This molecule is possible to synthesize from carbon dioxide. How? We can take aziridines, that is 3-member ring containing N, and expose these aziridines to the carbon dioxide. You get 5-member ring here, and this 5-member ring, now you can see that we get oxazolidones, and from oxazolidones we can produce several pharmaceutically important molecules. And these are named here. You can see that several molecules are possible. I have named here few. So using CO2 and aziridine reaction, we can prepare such type of molecules. Then benzimidazole, these are also important. This is also possible to synthesize from carbon dioxide. You can see that this CO here is coming from carbon dioxide. I will tell you the methodologies by which we have prepared all these molecules in next few slides. But right now you focus on the type of molecules which we can produce from carbon dioxide. Again, you can see that several pharmaceutically important intermediates can be produced using this backbone. So CO2 is our research focus, and we have mainly worked on these molecules which are circled here. We have prepared urea, salicylic acid, cyclic carbonate, then based on aziridines and also polymers. So many molecules which we have prepared from CO2. So let us focus on how we can transform CO2 into different value-added products. For example, this is epoxide and carbon dioxide. You can very easily cyclic carbonate using this technique. What is important here is the development of proper catalyst. So we have here graphene oxide catalyst in which NH2 group is docked, and this NH2 group is responsible for docking of carbon dioxide, and this carbon dioxide and epoxide will form the cyclic carbonate very easily. So the way we have prepared this catalyst is we have taken graphite Hammer's method we have used, then we prepare the graphene oxide, and this graphene oxide contains several hydroxyl group, and based on which we can dock this NH2 group very easily, and once we get the NH2 group on graphene oxide, carbon dioxide can interact with this molecule and you can get the product. So we can see that CO2 our catalyst and can give you the cyclic carbonate very easily. So TBAI is a co-catalyst, 94% yield, more than 99% selectivity can be obtained. This is a typical mechanism. It shows that how CO2 is docked and how it can go to the cyclic epoxide ring opening happens and how CO2 can cyclize and how product can be released. Given more details you can find in the publication. Again, this catalyst is recyclable. Whenever we develop catalyst, we are looking into the recyclability aspect. Otherwise, that catalyst has no meaning. We should able to recycle the catalyst. So here, this catalyst is very much recyclable and it retains its performance and catalytic performance. And it's even we have characterized this after 7th recycle. It retains all the properties which were there in the first cycle. So catalyst is stable during the reaction and you can see that it can happen. Look at the CO2 pressure, just 1 megapascal, 70 degree. Time was little bit higher, but we can produce cyclic carbonate using this particular technique. Next part, we have developed another set of catalyst which is useful for CO2 activation, that is N-heterocyclic olefins. These are N-heterocyclic olefins. This is an heterocyclic olefin based catalyst. So this is organic catalyst and that's why we call this as the organocatalyst. No metal is involved and it can react with CO2 to form such type of species which is useful. I told you aziridines. So this is the aziridine and you can see that this cyclic backbone is formed using CO2 very easily using such type of catalyst. We can take amines also. We can prepare formamides very easily using this particular technique. So this is the catalyst which is N-heterocyclic olefins or NHOs, and these NHOs are very effective in docking the CO2. You can see that CO2 molecule is docked here. So we have prepared, when we prepare these NHOs, we have taken into account of the varying the R1 and R2. So we get series of different types of NHO catalyst, and this is the aziridine backbone which we have prepared using CO2. So this is, you can see that, and there are two products are possible. Out of that, only one product is formed very selectively, more than 96-97%. Even epoxides, aziridines, all molecules are possible to synthesize using this technique. Next point, if you take secondary amides, you can also prepare formamides using this technique. This same catalyst, you need some reducing agent there and you can prepare formamides very easy. You can see that NH2 to formic acid. So formylation of amine is possible using this catalyst. Then our focus was also to develop biorenewable sources for the preparation of ionic liquids, because ionic liquid, again there is a debate going on whether they are really environment friendly. So we focus on developing ionic liquid based on biorenewable sources, and we have prepared similar catalyst. I would like to tell you one important point. We have prepared here aminobenzonitriles. These aminobenzonitriles can cyclize to give you this product, and this product is very useful in preparation of numerous pharmaceutical important intermediates. I will tell you that at the later stage. This is the biorenewable ionic liquid which we have produced from biological sources, and they are renewable. We have characterized, we have tested its thermal stability, and we can see that they are very much active for the epoxide to cyclic carbonate, aziridines to corresponding cyclicene. So this is epoxide to cyclic carbonate. It works. You can see that we can get the cyclic carbonate. Catalyst is recyclable. And this particular molecule, quinazoline 2,4,1H,3H diol, this finds application in several anti-diabetic drugs, and modification of this particular molecule gives you several pharmaceutically important intermediates. So again, CO2 is useful for preparation of various types of pharmaceutical intermediate very easily. Next part, after CO and CO2, we will see that how CH activation area is useful for pharmaceutically intermediate molecule. Again, carbon-hydrogen bond is one of the very strong bond, and how we can break and do the CH activation, that also we have to see. So there are some questions in chat box. After lecture, we will take all the questions in the chat box and we'll discuss. So let us focus on CH activation. Again, CH activation is very important because we can produce several bioactive molecules. For example, we can see that phenantridone skeleton which can be prepared by CH activation. So this red bond which you can see here is possible to prepare using CH activation technique. So how? We'll see that. See again some molecules, you can see that using this particular skeleton is possible with the help of CH activation. And how? We will see that in the next few slides. You can see that again biologically important esters which we can prepare. Then this molecule, again CH activation, carbonylation, all these techniques can combine to prepare such type of many biologically important and naturally occurring phenyl esters. So we'll see that based on that how we can use it. For example, we have developed here a technique in which we have developed palladium catalyzed deaminative phenantridinone synthesis using aniline. For example, lots of work has been carried out in the area of CH activation, but no one tried simple molecule like aniline. And aniline was challenging. So we have taken here aniline, and here there is one vanillin. So our report contains first time we are using aniline as a new source, and we did double CH activation. So we can see that two new bonds were formed. So this CH is activated, this NH is activated, and you can see that we could able to prepare phenantridinones very easily using this particular catalytic technique. Look at the condition, just 40 degree 18 hour, and water and nitrogen as a side product. So no other side product. If you consider conventional organic technique, you could have imagined lots of multi-step synthetic routes, small yields, whereas using this particular technique, we can prepare it in a very large quantity without any waste products or without any byproducts. So from that perspective, it is very useful. So synthetic approach for penanthroidins, which I had mentioned just now, multi-step synthesis and many more drawbacks were there, which we had eliminated in our work. And we can see that many new such molecules were synthesized, and N-methoxide benzamide was our starting material, and we could able to prepare using CH activation technique. We have also varied the aniline counterpart. Again, this was effective. So we can vary various substituents on this side, also on this side, and both are giving good yields with respect to the CH activation functionalization. Same way, you can have N-substituted benzamide. So here we have substitution here, but again you can do that and prepare the benzamides. Now, if we take such type of molecule, we have seen that only this bond is formed, not the cyclization happens. When you take here methyl, here methyl. So this H is not there. That's why you don't get the cyclization. You get another product. So you get substitution here, new bond formation here. And we have proposed the possible mechanism. You will get more details in the publication, how this mechanism we have proved, what sometimes we proved it, sometimes it depends on the type of reaction. We have postulated it, so we could able to synthesize such type of CH activation molecules very easily. Now another example of CH activation, herein we have used ruthenium PEG, which is a homogeneous catalyst. Now homogeneous catalyst which is recyclable, green, because PEG 400 is a green solvent. Catalyst can be recycled several times. So again, this is a green method, and we can see that we have constructed CC, CO, CN bond and via CH bond activation using this in this particular publication. We can see that we have taken here ARO, COR. Suppose this is reacted with the olefin, you can get the bond formation here. This is not formed, only this bond formation is here. If you take alkyne, you get double CH bond activation and you can produce this cyclically. If you take alkyne, suppose this is PH, again this is PH, you can see that you can get this. In this case, R is varied, and in this case, ROH, instead of NH, you get O here. Previous reports, when we started this work, were existing based on the rhodium, and many organic solvents were used, and the catalyst was not green. So what we did, we have substituted rhodium with cheaper ruthenium. The cost difference is 10 times. So from that perspective, this is inexpensive catalyst. Also, we have changed organic solvent into green solvent, that is PEG 400. And we can have such type of substituted products very easily. So we have seen that this is the optimization study which shows that very good yield with respect to this particular reaction condition. We can see that cyclization can happen very effectively using this particular technique. So all annulations you can do, ruthenium catalyzed. So that we have performed, and many new molecules were synthesized. Even you can take here Me, and you can see that this is PH, this is coming from this side, and you can see that new CH activation bonds were formed. The catalyst, how one can recycle. Here we have used interesting technique how to recycle this catalyst. As I told you, this is homogeneous catalyst and PEG catalyst. So what we did, we performed our reaction and we found one solvent that is N-hexane. This is not soluble here. So this solvent used to extract your products, whereas catalyst used to remain in the PEG solvent. So all your substrates and products were extracted into the another solvent, and then you use it, and the catalyst can be recycled further by phase separation. So n number of times you can use this catalyst by using this separation technique. We have seen that you can see here catalyst can be separated and recycled n number of times, although during the reaction the catalyst acts in a homogeneous manner. After the reaction you can separate it very easily. So we have seen several separation techniques. One is precipitating product. Here we have seen that we are extracting the reactants and products, and catalyst can be recycled. There is one more way by which you can recycle the catalyst, that is you can distill out the reactants and product. That is happen in the case of methanol to acetic acid synthesis. One can also anchor the catalyst on some support. You can again prepare the heterogeneous. So although you are practicing homogeneous catalysis, you can separate the catalyst by various means and you can recycle it, and you can in the both the world, that is heterogeneous catalyzed and homogeneously catalyzed. So that is possible using such type of transformations. So this is a reaction mechanism. Typical reaction mechanism involves, and all the steps which I had mentioned to you earlier, they are present in this particular reaction mechanism. We have seen CO2 and CH activation. Now we will see another application, that is how carbon monoxide and hydrogen together can be useful for preparation of different types of molecules. And this is syngas chemistry, which we will study. Quite often we need to have such type of transformation. For example, I have taken here internal alkyne and using palladium catalyst and syngas. We know the catalyst which poisons, and that is Lindlar, and many more catalysts are known which can give you this transformation. But herein I use syngas because syngas used to poison palladium, and I could able to selectively reduce this alkyne to alkene using this technique. So syngas, although not used as a reactant but used as a partial poison for the hydrogenation catalyst and do the hydrogenation, I showed it in this particular application. So various catalysts were screened, even palladium on Lindlar also we have tested. So in all the cases we could able to get the substrates very effectively using this particular technique. Now we have developed here another technique by which we can prepare 1,3,5-triazines. You can see that, and construct such type of triazine using catalysis. For example, I can take benzylamine, okay, and in presence of PEG catalyst containing ruthenium, I can couple this to produce 1,3,5-triazines in very good yields, which you can see in this particular publication. So we can see that different types of such triazines were prepared using this particular technique. So all the many more new molecules were synthesized. Oxygen is required and cesium carbonate is the base which is required in this particular transformation. Then we have also synthesized substituted alkene by direct coupling of alcohols and styrene. And here we don't need any catalyst. For example, just acidic ionic liquid like NMPHSO4 can be used, and we can see that how we can couple this. This is alkene, styrene and alcohol. We can couple them very easily using acidic ionic liquid. We can see that this coupling product is formed and very good yield was obtained. No metal is involved, no additive, no solvent, Just take these two substrate and NMPHSO4 ionic liquid, you can couple and form such type of alcohol and alkene coupling product. Similar way, this epoxide, if you take in a 2 moles and react with NMPHSO4, you can literally do the cyclization and you can get 2 phenyl naphthalenes very easily from styrene oxide. Otherwise, you can imagine that by conventional technique it is very difficult, but using acidic ionic liquids, it is possible to do this transformation. As I told you, we are working on nanoparticles chemistry. So we have developed different techniques by which we can prepare copper oxide nanoparticles. So herein we have developed a method in which copper acetate and microwave heating and 1,4-butanediol, which is a capping agent as well as reducing agent, you can see that as the reaction progresses, we could able to prepare copper oxide nanoparticle, and this we have used for Buchwald-Hartwig amination reaction. We can couple this very easily in very good yield using this particular technique. Same way, copper oxide nanoparticle. Now, earlier we have used here 1,4-butanediol, so we got this shape. But when we change the diol to propanediol, we got another shape. So by changing the solvent, you get the different shapes of your nanoparticles. This particular catalyst was used for Sonogashira coupling reaction. So again, I told you the importance of this particular molecule earlier, and we can prepare it using nanoparticles also. Then here we have produced copper catalyzed benzimidazolone synthesis using nitroaniline. For example, you can take nitroaniline. If you take here diamines also, it works. Nitroaniline also works. If you use nitroaniline, you need some reducing agent, and in this particular case, Kmhs, which is a typical hydride source, which can reduce this nitro to amino. And when you have amino here, you can do the coupling with dimethyl carbonate, and you can produce benzimidazolones very easily. And again, this is a very green route for synthesis of such type of heterocyclic molecule. In another work which we have produced with Oliver Reisner's group in collaboration with Germany, we have produced trimethyl chlorosulfonation of alkenes, and in this case we have developed a copper phenanthroline photoredox catalyst. Using photoredox, we could able to prepare this molecule. So photocatalysis also we have worked. We have also prepared silver chloride nanoparticles, and sugarcane juice was used, and this particular catalyst was useful in degradation of azodides. Very easily you can do the degradation of azodides using these silver nanoparticles which we had prepared. Then in this case we have developed vanillamide, double vanillamide for amino carbonylation of aryl iodides. For example, you can take aryl iodides, CO, palladium catalyst, and you can prepare amides. But if you take diiodo, you can get here diamylo. And such double carbonylation is also possible. If you have more alkyl halides group, you can do the introduction of carbon monoxide there also. So it depends on what type of molecule you are choosing. As I told you earlier, we had prepared 1,3,5-triazines. Again, from alcohol also you can prepare that. You need to do the oxidation of alcohol, that is possible with NIS, and once they oxidized it to the aldehyde, here coupling happens and you get the 1,3,5-triazines. Here we have developed chiral fluorescence active probe, and which is an efficient catalyst for asymmetric Friedel-Crafts alkylation of indol derivatives with nitroalkanes. So this is nitroalkane, this is indol, and we could able to prepare this chiral transformation of Friedel-Crafts and we have developed this method. This is published in Catalysis Science and Technology. Again here, coupling of this is CH activation work. You can see that coupling happens here with the alcohol, and you get very easily coupling product. So benzylamine and alcohols were reacted. Here Sonogashira coupling with copper oxide nanoparticles. We are also active in enzymatic catalysis. So we have developed a catalyst that is biocatalytic activity of Burkholderia cepacia lipase immobilized, and this was used for esterification. And this catalyst is again recyclable. Again here also we have prepared esters very easily using lipase catalyst. So many more such type of examples are there. By the way, if we develop catalyst based on iron, that is what is required, because iron is very inexpensive, easily available. So we have attempted iron catalyzed synthesis of aryl benzothiazoles. So you can see that this is coupling, and you can see that this olefin is coupled here in presence of iron catalyst very easily. Same way, we can do the reduction of these olefins using formic acid in presence of palladium nanoparticles. We can see that this is reduced. Again, based on silver nanoparticles which we have prepared, and we have reduced this nitro group to amino group, so para-nitrophenol to para-aminophenol using gold nanoflowers which we had prepared. Then MnO2, another important catalyst, very simple, inexpensive, and you can prepare coupling of these two, and you can prepare coupling product with MnO. Palladium on carbon, again you can prepare amide. Now here, ammonia is used as a surrogate to prepare this particular amides. Again, nitro to amino using palladium nanoparticles, and this is the reducing agent here. Here silica supported palladium phosphate as a reusable catalyst for alkoxy carbonylation, amino carbonylation. So you can take here, you can prepare amides, esters using this particular catalyst. Here you can prepare polyamides using this particular technique. So you can take diaryls and diamines and use CO using palladium on carbon. You can literally prepare polymer using this particular technique. So carbonylation technique for polymer synthesis is used here. Now quinazolines are also very important. We will find many types of quinazoline molecules, and which we could able to prepare using this coupling with amidins. This is amidins and halobenzoic acid. You can couple them and you can get the quinazolines very easily using this particular technique. Again here, base catalyzed synthesis of amides and imines, and you can, this is possible with the help of CC and C double bond C bond cleavage. So you can take beta diketones and you do this cleavage and you get corresponding amides very easily. Just KOH is required. Now from pharmaceutical point of view, this is very important. For example, suppose you want to have kinetic resolution. This is secondary alcohol, and using enzyme, we have developed a method by which you can do the chiral resolution, kinetic resolution of secondary alcohols using this Burkholderia cepacia lipase, which is immobilized on biodegradable tertiary blend polymer matrix, and this is heterogeneous recyclable biocatalyst. So you can have such separation very easily using this particular enzyme. Also here you can do the rhodium catalyzed synthesis of quinolines and imines under mild condition. So you can prepare quinolines very easily. You can see that here we have olefinic group, alcohol group, and amine group. So we can literally form a skeleton here, and we can get quinazolines very easily using this technique. And for that purpose, we use rhodium TPPTS catalyst. Now, what is this TPPTS catalyst? In the TPPTS catalyst, this is nothing but the sulfonated triphenyl phosphate. So you do the reaction, your catalyst will remain soluble into the water phase, and the reactants and products will remain in the organic phase. So biphasic catalysis you do, and since the catalyst remains in the water phase, you can recycle it n number of times, and in the organic phase your organic reactants are there. So this such type of biphasic catalysis you can do very easily, and homogeneous catalyst can be recycled n number of times. Also, you can see here esterification using enzymatic catalysis. Here we have prepared oxidative palladium catalyzed oxidative synthesis of aromatic ketones, which we had already discussed. And using palladium chlorine and TBHP as an oxidant, you can have so olefin plus this is a group here DG, that is pyridine, and pyrazole group is there. You can have CO here. Here carbonylative synthesis of thaliamides and benzoxazinones using phenyl formamate as a carbon monoxide salt. Every time you should not use carbon monoxide. There are substituents for carbon monoxide, and they are called as CO surrogates. So if you find that using carbon monoxide and high pressure autoclave is a difficult task for you, you can use such surrogate molecules, for example phenyl formate. We have done lots of work on CO surrogates, so no need of autoclave. You use these molecules, they will give you the CO transfer. So here we can see that phenyl formate is a CO surrogate, and we can able to produce benzoxazinones very easily. You can see that this coupling, this is the carbonylation point, and NH cup activation. So both happens, and you get such type of molecule. What this CO is derived? This CO is derived from formate molecules. So instead of CO, you can use surrogates also. That chemistry is also possible. We have published lots of work on CO surrogates. Okay, you can also synthesize vanillamides. Vanillamides is a class of molecule which needs lots of application, particularly pharma intermediates. Again, you can do that using copper, TBHP, and calcium carbonate. You can see that vanillamides were synthesized. If you use tertiary peroxybenzoate and use benzoylation of ammonia or amines, you can again produce such type of amides very easily. So here amines leaves, and you get such type of substituents. So lots of other work. You can see that this coupling happens here, and we could able to produce benzothiazoles using zinc catalyst, and benzimidazoles and benzothiazoles. So suppose you take OH here, you get benzothiazoles. If you take NH2 here, you will get benzimidazoles. And using zinc catalyst, it is possible. So if something interesting found, I will focus on. In this case, we have done 3-component coupling reaction, and nickel oxide nanoparticles were used, and alkyne, amine, and aldehyde, and you can get propalgyl amines very easily using this technique. Same way, we can do the cyclization, which I had mentioned to you earlier. In this case, we have prepared iron oxide, which is a nanoparticle iron oxide, and since it is iron oxide, it is magnetically separable iron oxide because it is a gamma Fe2O3 form. And this was used as a catalyst for acylation of alcohols, phenols, and amine. So you can take any phenol, alcohol, or amines. You can take acetic anhydride, and you can do acylation using this particular catalyst. And just put a magnet. Catalyst gets separated, attracted towards magnet, and you can separate your reactants and product in the liquid phase, and you can recycle them again and again. So this technique which we have developed, and during acylation we use sonication. So reaction happens at ambient conditions very easily, and this particular work is focusing on how magnetically separable iron oxide can be used as a catalyst for acylation of various alcohols, phenols, and amines with acetic anhydride. Again here, olefin and alcohol, we can form the esters using lipase enzyme. Geranyl acetate was synthesized using lipase. Again, lipase-based esterification, and here we have produced different molecules. In this case, hydroalylation of paracresol with styrene was performed. We can see that this can couple here very easily. So some kind of CH activation, and you need only Montmorillon nitrile K10 catalyst 80 degree. You can have coupling here. You can see that this couples very easily. I mentioned to you CO2 to quinazoline 2,4,1H dions. It is possible. Another catalyst was developed here to prepare such type of molecule. Something important, chemoselective transfer hydrogenation, fine. Synthesis of polyesteramide I had discussed. This is different catalyst, another polymer, but different catalyst using carbonylation. In this case, again, we have performed another study in which you can do this chiral resolution very easily using different type of catalyst. In this case, we can see that alkyne CO, and you can take either aryl halide, diaryl halide, or something. You can get the corresponding carbonylation products very easily. And we have developed heterogeneous palladium anchored catalyst which is recyclable. This is quite interesting. Here we have used chiral phosphoric acid catalyzed asymmetric transfer hydrogenation of quinolines in sustainable solvents. So we can see that this is particular molecule of interest, and we have reduced this part using chiral phosphoric acid, which is showed here, and we can see that we could able to do this very effectively, and you can produce this chiral center in good enantiomer selectivity. So finally, I would like to thank you for your patient hearing to me. I have shown you so many slides, but the important point is my focus is on catalysis, how catalysis can reduce multi-step synthesis into few steps, and giving you more environment-friendly approaches towards synthesis of many molecules, and many of them are important in drug synthesis. A classic story is ibuprofen, which I had not showed here. Probably many of you have heard it. Ibuprofen synthesis initially used to involve multi-steps. After that, you know that using carbonylation and palladium catalyzed reactions, it became into very few steps. There are many success stories in pharmaceutical industry in which green chemistry has played a significant role in reduction of resources, also multi-step synthesis, reduction of solvent, recyclable solvent. So we should focus our future attention on developing such type of techniques. I understand that there are some regulatory requirements. We cannot alter the current manufacturing processes, but at least in R&D we should focus on paying attention towards multi-step reduction of multi-step synthesis into few steps and the use of catalyst for such type of transformation. So I will be happy to have discussion with all of you, and if you have any queries, I will be happy to answer.
Thank you so much, sir, for that intriguing and thought-provoking talk for today. I would request chairperson for this session, Dr. Shrikant Ghorse, to summarize your talk, and then we would open the session for question and answer. Over to you, Shrikant sir.
Thank you, Ina. Thank you, sir, for wonderful presentation on various application of organic chemistry and especially metal catalysts. In this session, sir explained the various coupling reactions, CO activation, CO2 activation, CH activation, carbon monoxide and hydrogen application in the pharma, and then nanoparticle, especially copper and copper oxide, and also he highlighted some biocatalysts, green catalysts in this session. In CO activation, sir explained many API intermediate which are valuable product in industry also, and he tried to overcome the drawbacks of traditional method. And in CO2 carbon dioxide activation, sir also give the application of this CO2 in a proton pump inhibitor, that is omeprazole and benzimidazole drug, and he also explained the linezolid synthesis that require oxazolidine ring in this session. And in the CH activation, he also synthesized the many value-added product using palladium and ruthenium and using green solvent PEG. And the application of these catalysts in CC, CO, CN via CH bond formation. And interestingly, he also recycle homogeneous catalysts. That is very difficult. Normally, you can recycle heterogeneous catalysts. It is more easy, but homogeneous catalyst recycling is difficult as compared to heterogeneous, and in this lab he tried. So thank you so much for sharing this technique. And another in carbon monoxide and hydrogen application, he tried many synthesis in using that palladium PEG, and also he shared the green approach using ionic liquid. And in the hot topic, that nanoparticle, because in using that copper and copper oxide, in this he explained the backward amination reaction, Sonogashira coupling, and he also explained the that conversion of nitroaluline to benzimidazolone. And one more, he also used the nanoparticle of silver at silver chloride and sugar cane. And he also in the nickel oxide nanoparticle for the synthesis of alkane. And one more important synthesis I found in your presentation, sir, conversion of paranitrophenol to paraammonophenol. This is an important intermediate for the synthesis of paracetamol. And you try to convert using gold nanoparticle. Thank you so much, sir. Very nice presentation for sharing with us. We are happy. Most of the chemists are always happy with your presentation, because this is a huge work and industrial applicative work that really help for India, because we are lacking in many API intermediate synthesis. Because most of the API intermediate exported from foreign, for most of 60% from China. So for my question after this is how we overcome this drawback from our India side. Please give your suggestion. Will really help you a young faculty or young student from this session, sir. Thank you so much for your presentation.
Actually, let me tell you, our chemist behind there is point is pricing which they are getting is not competitive. So where there are many overheads with respect to electricity, manpower, and that's why our synthetic methods are not becoming competitive with respect to China. We can synthesize all types of APIs. It's not a problem.
Yes, sir.
So we have to see that how we can reduce our overheads. We have developed, our chemists have developed lots of new methods, lots of cut shots, and developed very nice economical methods. But the problem is with the overheads, and that makes seems these methods is not economically viable. Otherwise, here in India, I find that all these things is possible to do in India.
Yes, sir. Thank you, sir.
There is no scarcity of knowledge, there is no scarcity of manpower, everything is available.
Yes, sir. Now, we can take a question answer from participant. Please.
Yes, sir. We can take question answers from participants. There are a few questions in the chat box. Okay. Okay. So the first question is from our own faculty member, Dr. Archana Gurjar. Uh, she wants to say, sir, you spoke about iron catalyst and zinc catalyst. So can you comment on stability
They
of
are
them?
stable. They are stable. Stability of nanoparticle depends on the capping agents. The role of capping agents is very important. Depends on the type of capping agents which you are using, stability will be there. Otherwise, they are very energetic, quite often have tendency to agglomerate, where to avoid the agglomerization. So the concentration of nanoparticle is very important, first point, and that type of capping agent is also very important.
Okay.
Zinc and iron which she has asked, they are stable in our case.
Okay.
And
And in continuation.
one more point, when you use nanoparticle in solution form, please sonicate it so that they disturb very well. If there is any agglomerization, they get distribution, they get separated with the help of sonication, and you can use them for the reaction.
Okay. In continuation to it, she has asked, are they commercially available?
Yes, zinc I don't know, but iron is available. Otherwise,
Okay.
preparation methods are not difficult. Only problem with zinc, it's not a zinc oxide actually. It's not zinc oxide. Very difficult to prepare zinc oxide in very small nano size form. Typically 30, 40 is the typical range in which zinc oxide nanoparticles are available. If you want below 10 nanometer, I have not seen such procedures. Quite often they tend to agglomerate. Many oxides have this problem. Otherwise, metals you can find it very easily in the nano range of 0 means 1 to 10. Whereas oxides are quite often having a larger size as compared with metals.
Okay. Sir, she has also asked another question. If we compare homogeneous and heterogeneous catalyst, to start with, which one should be experimented?
See, the reaction which is possible using homogeneous is not possible with heterogeneous because conceptually they are completely different. Okay. Second point, only one reaction which I found is a common, that is hydrogenation. Hydrogenation you can do with heterogeneous as well as with homogeneous. But other reactions, they are classically homogeneously catalyzed reactions. So what you should think, how you can heterogenize those catalysts on some support, or find the techniques by which you can separate, which I had already mentioned in my talk, how you can do that. And heterogeneously catalyzed reactions are typically high temperature reactions. In refinery, you always find heterogeneous catalysts. If you consider the catalysis industry, 85% of the catalysis today in industry is with the heterogeneous form, and 15% is just homogeneous form. Why? Because fuel industry uses heterogeneous catalyst. So suppose you remove fuel industry, probably the contribution by homogeneous as well as heterogeneous may be equal.
Okay. I can't see any more questions in the chat box. Probably it was so intriguing and it was very clear. So, if any participants wish to interact with Sir, kindly raise your hand. We will offer the mic to you. Dr. Archana is thanking you for your answer.
Thank you.
Any participants who wish to interact with Sir? Kindly raise your hand.
Very much. It was a really wonderful session. And since the faculties are attending this session, I just I'm not a chemist, but I'm a pharmacologist. But I have one question that to promote research in the green chemistry, what funding initiatives are there by government of India?
No, government has special task force. Government has DST has constituted special task force on the green chemistry. So they invite proposals in this area. They do funding also. Government want to promote green chemistry because from environmental perspective it is very important.
Thank you.
Sir, I have a question from my side.
Sure.
Sir, can we use some sort of catalyst for, conducting the in particularly reaction for, like heterocycles like benzimidazole, benzotriazoles with, say, chloracyl chloride or, some similar chlorides where we are interested in, attacking at that nitrogen. So, you have shown for some tertiary amides, but if we want to, have that linkage with the nitrogen that is present in the ring, then can we use some of these methods?
Possible. What I showed you, no, you can extend it for your molecule because it's just an extension of what I showed to another molecule. Possible.
Okay, so it need not necessarily be an usual tertiary amide. We can extend it to the heterocyclic systems also, basically. Okay. Thank you so much, sir, for answering that question.
Someone has raised the hand. Someone has raised the hand.
Yeah, Dr. Archana Gurjar has raised the hand.
Okay.
Tina, can you offer mic to her from your side? Just quick.
Yeah, just a second.
Thank you. Am I audible?
Yes, you are audible.
Thank you, sir. A very enlightening lecture and the journey of all heterocycles. It was a wonderful session, sir. Sir, I wanted to ask you one more. I have lot of. I'll definitely on mail also, or will talk to you in person. Sir, you said about carbon monoxide that you need high pressure and conditions. So you commented about the surrogates. So
Yeah.
likewise, I wanted to ask you that for carbon dioxide activation and the CH activation which you spoke about, so like for them also we require like
No, no.
in the lab some setup. Can you comment on the setup for these two also, activations and CH activation and
Sure,
carbon dioxide
sure.
activation?
I will talk on that. See, for carbon dioxide, you can take CO2 balloons very easily. You can prepare. You don't need high pressure equipments. Second point, for carbon monoxide, as I already told you, you can use surrogate molecules. For CH activation, you don't need anything. Seal tubes are enough to do the CH activation experiment. You don't need any sophisticated setup to do all this type of chemistry.
For carbon dioxide, what did you say, sir? I couldn't hear because of the connectivity thing.
Carbon dioxide balloon you can use. Balloon
Oh,
chemistry.
okay, okay. Just like we use the nitrogen air balloons and these for of inert gas.
Yes, you can use that.
Okay, okay. Thank you very much, sir.
And CO2 is not at all toxic, so it is safe to use.
Yeah, as compared to carbon
Carbon
monoxide, that is a
monoxide
problem.
is a toxicity issues are there, but with CO2 those issues are not there.
Okay, okay, okay. So in the lab setup, and the scalability also will be, as your papers are there, so definitely the scalability will be
And
there.
many of these reaction works at atmospheric pressure, so balloon chemistry will work there.
Okay, thank you very much. A very enlightening session.
Any other participant who would like to interact with Sir? There are a lot of people posting that it was a very interactive session. It was quite informative. So I think, one second.
That I think that all queries have got solved. And I'm really thankful for one thing to the sir, that sir is so particular. He has cooperated us so well for this FDP. There was a sudden change in his schedule, but without any hesitation, he agreed for that. And I'm really thankful to you, sir, for that. Your cooperation has really helped us to make this FDP very successful. Thanks a
Sir,
lot, sir.
welcome, madam. No issues.
Hope we can to conclude this
Some
session.
question is there, ma'am. Hello. Sorry to
Yeah,
interrupt
yeah,
you.
yeah. Yeah, there is one question uh, from Vaishali Jadhav. How to optimize
Concentration of
concentration of
catalyst. Yeah.
catalyst? Yeah.
Say typically catalyst, if you are using, it should be 1% to 5% range initially. So initially you take maximum possible concentration. Maximum you can go up to 10% or 10 millimole, whatever. 10% of your substrate you take as a catalyst. If it works, you go down and see that at what lowest level you can work with it. For example, when I tried with palladium cycle catalyst, I already know that palladium cycle catalyst work at ppm levels. So I started with ppm level and I went down to ppb level. Can work that. You should have some prior knowledge about that catalyst.
Should we wait for a few more
Yes, we
minutes
have
so that
time.
if somebody has any questions?
Maybe still their thought process is
Yeah.
going on.
Probably this is a new subject for many of them, so they may need to think over it and all that. And that's why initially I took some basics about the subject.
Probably everyone is connecting to their research, how they can,
Yes.
get an overall connect with their thing and then ask.
Even what I find that conventional medicinal chemistry people, they do multi-step synthesis. They never bother about using the catalysis. And if they apply some concepts of catalysis, it really change the way they're preparing the catalyst, reactions or target molecules. You have seen that many of these molecules which I had projected here, conventionally it needs lots of multi-step synthesis. Just with few steps you can do that. They should
Yes.
communicate with catalysis chemists before finalizing their procedures.
And creating that awareness among the faculties. The research has to be focused now on these areas if you have to live in a good environment, on a healthy environment. Thank you very much, sir, for your time and the knowledge which you have delivered to us. I'm sure it is going to help the faculties to develop upon in their research area in field of chemistry. Thanks a lot for
Thank
all
you.
your
Thank,
cooperation.
Thank you. Thank,
thank you, sir.
thank you.
Thank you so much, sir, for that very enlightening session.
Yes.
I would like to request participants that we will be joining back for the second session of the day at 11:15 a.m. I see a lot of queries for the attendance. Don't worry, we will be posting it shortly. So hope to see you back soon at around 11:15. So that will be all after this very thought-provoking session. We will have another similar kind of session today in the next slot. So please join us. Yeah, that will be all. Thank you.
Thank you.
Thank you,
Thank you
sir.
once
Thank
again,
you.
sir. Thank you.